All right, this is the Laws of Logarithms Part 1. This has to do with looking at the properties of our logarithms that are going to allow us to combine, condense, or expand an expression out. So we want to look at what they are and then practice how to use the condensing down to a single log and then expanding out to multiple logs. So that's what we're going to be focused on in this video. So our properties are as follows. If you have two logs that have the same base and you are adding those two logs together, you can condense that down to a single log with the same base and you multiply the two arguments together. Or you can take a log that has this base A and an argument that has multiplication inside, and we can then split this into two separate logs with that base and the two separate arguments. So it goes either way. This is kind of analogy to when you had x to the second times x to the third, and you said that was x to the 2 plus 3, which is 5. So notice multiplying same bases, we added the power. So this is a relationship here to that with logs. So then log a of x minus log a of y. Notice this time we're subtracting and we have the same base of our logs. This turns into division of the two arguments, and it's always the first one over the second one. A key way to figuring out which one's on the bottom, the log that has the minus sign in front of it is going to have the argument that's in the denominator. And then the final one is if you have a log with a base in the argument that has a power on it, we can bring that power to the front as a coefficient that is multiplied times the whole log. This is a really useful property. We'll use it when we solve some logs later on. You'll want to be able to pull powers to the front, especially with application problems. A lot of times that may be how you get your variable out of the exponent. So this property is a really important one. So we're going to look at two different things. Today we're going to condense some logs into a single log, and then we're also going to expand a single log into a bunch of logs that have been added and subtracted together and have a singular argument inside. So that's going to be our goal. So if we're condensing log expressions to a single log, step one, any coefficient in front of a log expression should be placed on the argument as a power. So in other words, you look in front of each of your logs and you say, okay, are there any multiples or coefficients in front of them? If there are, we need to put those back in to the inside as a power, just like this rule right here, the third one. Step two, we'll condense any adding in between two logs into one log with multiplication of the arguments and any subtracting between two logs with the same base into division of the arguments. So we're going to start off with some easy ones and work our way up. So this first one, notice these are both log base 10. Remember, base 10 is not always written for us. So since they have the same base and we're adding between them, we would rewrite this now as log base 10 still of 3 times 5, because that's my two arguments, which would be log base 10, or just log, of 15. So now this has been condensed into a single log. Okay, so look at our second one here. These are both natural logs, so base e. This is subtraction between them, so we'll write this as natural log. Notice it's just a single natural log. And then inside, since this was subtraction, we're going to do the first one's argument divided by the second one. So 14 divided by 2, or natural log of 7. Okay. For the next one, notice there's a number in the front. So none of these had any numbers in front of their logs, so we were able to just combine adding and subtracting into multiplication of arguments and division of arguments. This one, though, has a coefficient up front, so our first step is going to be to place it back up top as a power. So this would become log 2 of 4 to the third, and then typically we would work this out. So 4 to the third is 4 times 4, which is 16, times another 4, which is 64. Now, we're not actually solving any of these for decimal answers or just an exact answer of anything. We're just trying to condense them down to a single log. Okay, so let's look at this next one. This has a 1/3 on it. So let's talk about, that's again a coefficient out front. So we'll put that back on it as a power. And it's going to go on that whole binomial. So this is going to be log base 3 of 2x minus 1 to the 1/3 power. And typically we don't leave that as the 1/3 power because we remember that rational exponents are radicals. So that would be the cubed root of 2x minus 1. And there we go. Okay, so jumping from some of these that had just a single property to apply, we're now going to look at one that has quite a few things going on. So for number 5, the first thing I'm going to check for, since there's multiple operations and I see lots of numbers, is I'm going to look to see if any numbers are in front of any logs. And I see a 7 in front of the first log and a 1/2 in front of this log right here. I know there's a negative in front of it. Remember, the negative is going to be one of our properties, so that's a subtraction sign. So if I put this 7 back up on that x and the 1/2 back up on this x minus 3. So this will be log base 2 of x to the 7th plus log base 2 of x plus 1 minus log base 2 of x minus 3 to the 1/2, which I can write that as the square root of x minus 3, and I probably will in just a second, but I want to go ahead and try to finish up what I can here, and I'll simplify that at the end. So these two logs right here are back to back, and they have a plus sign between them. So remember, if you have a plus sign, you combine it to multiplying the arguments. So this would be x to the 7th times x plus 1. Bring down the minus log base 2 of x minus 3 to the 1/2. You could go ahead and distribute that. You won't always have to do that, especially if the x plus 1 has a power on it as well, then we would leave it factored. But since it's just a x plus 1 to the first, I might just go ahead and distribute it. So that's x to the 8th plus x to the 7th, and then minus log base 2 of x minus 3 to the 1/2. Now this has a minus sign between these two logs, so that means we're going to change this to one big log. You don't need two logs anymore. And it's going to be the top divided by this bottom. Now, in this scenario, I did distribute that x plus 7. I might pull it back out just because it'll look cleaner. It'll look like we factored everything. And then this bottom part is the argument from the second part. So that's square root of x minus 3, since it's to the 1/2 power. So I've made this big group of adding and subtracting logs, all condensed down to a single log with that base 2. And we did all of this just using those 3 properties. Okay, let's try another one. So this one's a little different. Notice this guy has a 2 in front of a bracket, just to complicate it a little bit more, so we have to think about it. You could distribute the 2 first, the negative with it. I would distribute that. Or you can combine this first and then apply the 2 on there. So sometimes the step 1 and step 2 are not fast, hard rules if you have some operations that you have in a parentheses. Because typically in order of operations, we would do the parentheses first. So I'm just going to make that something I don't have to worry about by just distributing the negative 2, because then everything's just easier for me to look at. Now when you distribute, you do not multiply it times anything in the arguments here. It's going to go in front of each log. So that's negative 2 log 4 of 2x and negative 2 times 1. So that'd be negative 2 log 4 of x squared. Okay, so because there's 2's in front of each of these, I'm going to put them back on the arguments as powers. So this would be minus log 4 of 2x squared minus log 4 of x squared squared. So we can simplify some of this down. This is log base 4 of x plus 2 minus log base 4. Now you're having to square both the 2 and the x, so that's going to be 4x squared. And then minus log base 4 of, this is 2 times 2 because it's power, so that's going to be x to the 4th. Okay. Now, here's something I like to talk about in my class. Yes, I can do this in pairs. I would have x plus 2 over 4x squared because of the minus sign. But if you have any log with a minus in front of it, it ends up that argument's going to be in the denominator. So instead of beating your head over making a fraction and then making another fraction because of the second minus sign, I always tell my students you can shortcut to this is going to have the x plus 2 on top because that one had a positive log in front of it. And the other 2 arguments are going to be on the bottom because they had negatives in front of their logs. So subtraction ends up being on the bottom. And notice down here, these two are being multiplied. That's because if you pulled out a negative out of this, like as a GCF, you would see that you have a minus, and then inside you would have had addition. So that's just something to realize, is that this is a shortcut for that. Now I can simplify the denominator a little bit. This would be x plus 2 over now 4x to the 6th if we add our exponents. And that one is our answer for number 6. Okay, let's look at number 7. Looks like we have another case where we have minus minus, so let's use our rule that we just talked about there. No numbers in front of any of them. They're all ready just to be combined. They're all the same base. So if I use my rule about positive logs have arguments on top and negative logs have arguments on the bottom, this would be x over y squared z. Because this log has a positive in front of it, so it's going to have an argument on top. Both of these have negatives in front of them, so their arguments go to the bottom. Okay, so that's condensing logs, so putting them all these different logs together into a single log with that one base. The next part is going to be expanding logs, so breaking them back apart. We want to be able to break them apart until we get to a point where each log has a single piece of information in its argument, like a variable or a number or a binomial possibly. So the first thing we do, so we do this kind of in the opposite order. We break apart any division into separate logs with subtraction. We break apart any multiplication into separate logs with addition. You may need to distribute a negative here if there were any multiplications that were in the bottom of a denominator, or if you know my trick, you know that if it was in the denominator, it's going to be a negative log. If it was in the numerator, it's going to be a positive log. And then we bring any powers of the arguments to the front of the log as a coefficient at the very end. So let's look at this first example here. We have log of x times z. So if I wanted to break this up, this one's pretty simple. Since they have a multiplication between their two arguments, we would break that up into log of x plus log of z, using the addition to multiplication of argument rule. For the next one, it's big natural log, and it's got division, so that means when we break it apart, it should be subtraction between them. So natural log of x plus 1, since the top one always comes first, minus natural log of 2x minus 1. So that's our first two. So we've expanded those out. And I know I'm done because there were no powers on any of my arguments, and I don't have any multiplication or division inside any argument. Now, a lot of people think you can break the plus and minus up and break those into separate logs. You cannot. The only time you can break an argument into separate logs with the same base is when you have multiplication or division inside. So let's talk about number 3. There's no multiplication or division inside per se, but there is a power of 4. So we're going to bring that to the front. So this would be 4 log 2 of x. Now you could have wrote that as x times x times x times x and then broke it up into 4 log 2 x's and then added them all together and got the same thing, but we like the power rule because it gets us there a little bit quicker. This next one, notice this is a cubed root of x, so we'll want to write that as a fractional power because we want to be able to bring the powers to the front. So this would be x to the 1/3, and we bring the 1/3 to the front of the log. So 1/3 log 3 of x. Notice we have a singular base with no power inside. Okay, for number 5, we have multiple things going on. So I'm going to break this division up first. So this would be natural log of everything on top minus natural log of everything on the bottom. Then because this has times in it, I can break this up again. This would be natural log of x squared plus natural log of z. Bring down the minus natural log of y to the 3rd. So I broke up my division first, then any multiplication. And now I'm going to bring any powers I see to the front. So there's a power and there's a power. So this would be 2 natural log of x plus natural log of z minus 3 natural log of y. So this has been expanded out as far as it can. Okay, number 6. Again, I'm going to break up the division first. So this would be log base 5 of 2z minus 1 to the 2nd minus log base 5 of x cubed z to the fourth. The reason this one's a little trickier than number 5 is because the multiplication is happening in the denominator. Now, if you remember my little trick I told you a minute ago, you know that each of those logs, when I break them apart, should be negative because x cubed and z to the fourth both came from the denominator. The way we show that algebraically is that when we go to split it, we have to realize, oops, sorry, let me fix that real quick. That is a 2z minus 1 squared. When you split it, you have to realize that that negative is going to apply to anything you get, so it's going to be distributed. So this would be log 5 x cubed plus log 5 z to the fourth, if we use the fact that times turns into plus of the two logs. So then we would distribute that negative to both of them. So minus log 5 x cubed plus log 5, or excuse me, minus, see, talking and writing is hard. So minus log 5 of z to the fourth. Okay, so that's distributing that negative to both of those. And then we would want to pull our powers to the front. So this would be 2 log base 5 of 2z minus 1 minus 3 log base 5 of x minus 4 log base 5 of z. And that's expanded out as far as we can go. All right, I believe I have one more just to get us some more variation. Again, split up the division first. So this would be, and you have to notice when we do this, we make everything we split have that same base. So log base 3 of x, and I'm going to go ahead and write this guy as x minus 1 to the 1/2. That'll save us a step later. And then minus log base 3 of 2x minus 3 to the third. So I'm going to split this times right here into addition. So this would be log base 3 of x plus log base 3 of x minus 1 to the 1/2. Bring down everything else. Notice that I did not need to distribute a negative here because the multiplication happened on top. And then we're going to finalize this by bringing any powers to the front. So this would be plus 1/2 log 3 of x minus 1 and minus 3 log base 3 of 2x minus 3. Okay, that is the end of this video. Hopefully you're feeling a little bit more confident with the properties of logarithms and how to use them. The ones that we use the most in college algebra are typically when we try to condense it back down into a single log. That seems to be a lot more useful for solving equations. So you'll notice we use that a lot in the next video. So you do have to know how to do this. The most important things in Chapter 5 are understanding how to convert between log and exponential form and essentially knowing how to use these properties to help you break things apart or put them back together. All right, that's the end of the video.